Let's take a look now at Chapter 3, which is all about solar and terrestrial radiation. Our driving question here is, how does energy flow into and out of the Earth atmosphere system maintain Earth as a habitable planet? Let's start off by reviewing the electromagnetic spectrum. Electromagnetic radiation is emitted by all objects. We cannot see electromagnetic radiation, but it's a theory that describes how energy from objects is emitted. Through part magnetism and part electricity, we have this word electromagnetic radiation. And we can imagine that the energy travels via wavelengths. And you see here in the red picture of a longer wavelength, and then in the purple a shorter wavelength. Wavelength is the distance between the crests of a wave. We have the crest, which are the high points, and the trough, which are the low points. For any particular wavelength, it's going to be constant. So energy that's emitting at, say, this wavelength, it's always going to be the same wavelength. And so we can define it by the actual wavelength that is measured here. You can see the longer wave versus the shorter wave. This is a shorter distance here. All electromagnetic energy travels at the speed of light, which is 186,000 miles per second. And we see here the entire electromagnetic spectrum with the shorter wavelengths towards the bottom and the longer wavelengths towards the end. Longer things being radio waves, shorter things being gamma waves, and everything in between here. And you see the corresponding wavelength values in meters. And we have the visible light spectrum, which our eyes are attuned to work at. We can see visible light. That's why it's called visible light. And you see that it ranges from about 0.4 to 0.7 micrometers, from purple to red. So our sun emits between 0.2 to 9 microns. So that, as I said, spans between the ultraviolet and the infrared range. And here's the breakdown. It's about 8% ultraviolet, 47% visible light, and then 45% infrared. There are a series of 3 radiation laws that we use to describe how radiation behaves in the Earth atmosphere system. The first one is simple. It just is a definition, really, of a black body. And a black body is something that is a perfect absorber and emitter of radiant energy. So it absorbs all of the energy that's cast upon it, and then it re-emits all of that energy. It doesn't store any. And we can say that the sun and the earth are both nearly black bodies. So then the second radiation law is something called Wien's displacement law. It is the wavelength of maximum emission is equal to some value c, which is a constant, divided by T, which is temperature. So in other words, the wavelength of maximum emission is inversely proportional to the temperature of the object. So in this diagram here, we have the wavelength, so shorter waves are more energetic than longer waves, and then the intensity, some measure of how much energy is coming out. And then these values that you see on the curves are temperature values in degrees Kelvin. We'll talk about temperature in an upcoming lesson. So the hotter the object, we see by this curve here, the shorter the wavelength of maximum emission. And vice versa, the cooler the object, the longer the wavelength of maximum emission. So something like the sun, which is 6,000 degrees Celsius, compared to the Earth, which is 15 degrees Celsius on average, that means that the sun emits energy at a much shorter wavelength than does the Earth. So the hotter the object, the shorter the wavelength of maximum emission. That's Wien's displacement law. The third radiation law is called the Stefan-Boltzmann law, and it basically says that the energy emitted by an object, by a black body, is proportional to the 4th power of its temperature. So the formula is a little more complicated than that. So instead of having an equal sign here, we have is a proportional symbol. So we're saying that the energy emitted is proportional to the 4th power of the temperature. In the graph here across the x-axis we have wavelength, and on the y-axis we have flux in watts per square meter, a measure of the radiant energy. And we have here a measure of the sun's energy. The solid dark line shows the amount of energy that would be radiated based on the radiation laws, and the red shows actual measured values. So 6,000 degrees Celsius body like the sun would expect to put out a spectral imprint like you see here. On the right we have the same thing for the Earth. Notice the x-axis now is in micrometers. The temperature of the Earth is much lower, and so the energy distribution is over a lower portion of the spectrum. The sun is composed primarily of hydrogen and helium, and the energy that the sun generates is from nuclear fusion. So there's a lot of nuclear explosions happening on the sun that keep it hot and send its energy to us on Earth. The part of the sun that we see is called the photosphere, and it's much cooler than the interior of the sun. And then we can also see sunspots with the help of telescopes. Sunspots are actually cool areas on the sun's surface, but they're always accompanied by brighter areas called faculae. And the number of these sunspots and their corresponding faculae vary over the years. There are cycles of intense activity and then cycles of lower activity. This year we happen to be in a cycle of intense activity. The chromosphere is the sun's atmosphere, and you can see the chromosphere if you've been fortunate enough to see a total solar eclipse where the shadow of the Earth blocks the disk of the sun and you see the corona outside of that. Solar altitude is a degree measurement of how high in the sky the sun is for a particular location at a particular time. So we have a sun that can be directly overhead. That's the highest that the sun can be. So if the sun is directly overhead, the energy that it's shining down on the Earth is going to be concentrated in a smaller area. And you see that in the picture here with flashlight A. So it's directly overhead, it's shining down on the surface, and the amount of energy is contained in this bright white circle. Compare that to a lower solar altitude. When the sun is lower in the sky, closer to the horizon, the energy is coming in at an angle, and it intersects the Earth in a way that causes the energy to be dispersed over a larger area. So we may have the same amount of energy coming in, but it's being spread out over a larger area. So we have more intense energy coming when the solar altitude is high in the sky compared to when it's lower in the sky. The distance between the Earth and the sun is so far that for all intents and purposes, we can imagine that the solar radiation coming on the Earth is coming in parallel lines. So when you see these lines drawn like these yellow ones here, this is assuming that the Earth's radiation is hitting us in these parallel lines. And then same thing over here, it's just showing them as red wavelengths to emphasize that it's electromagnetic energy. So when the sun is directly overhead for an area, like it is here at the equator, the amount of atmosphere that radiation has to pass through is much less than for areas further towards the poles, for which the sun has to pass through a thicker layer of the Earth's atmosphere. So not only do we have that flashlight effect that we saw in the previous slide, but we also have the energy passing through the atmosphere. And as we'll see in a moment, the atmosphere presents a lot of different surfaces and gases that disperse some of this energy. So the more atmosphere the solar radiation has to pass through, the less of that energy that's going to reach the surface. So here we see the solar altitude at different locations at the equinox times, the vernal or the spring and the fall equinox. So on those equinox days, the sun is directly overhead at the equator. And so at solar noon, the solar altitude is 90 degrees. So we see that here. It's intercepting at a 90-degree angle. On that same day, at solar noon, at different locations, you see that the angle becomes less as we move poleward. So that angle will never be more than 90, and it varies between 90 and 0. In this picture that we see here, there are 3 locations. One at Antarctica, which is on the pole, the South Pole, one for a mid-latitude location in New York, and the third one for a location pretty close to the equator. And across the x-axis we have months, and on the y-axis we have the average daily solar radiation in some units that represent energy amounts. So for the mid-latitude areas, which we're most familiar with, we have much more energy coming in the summer months than we do in the winter months. So we see a typical profile like this green line here. For areas closer to the equator, the sun is always relatively high in the sky, and so the energy amount received in the tropical areas is relatively constant throughout the year, as we see it here in the red line. And then finally, near the poles, where we have periods of darkness, for the South Pole, it's dark throughout the summer months, the northern hemisphere summer, which is the southern hemisphere winter. There's no sunshine at all at the poles, so zero solar radiation receipt. And then when it becomes summer for the southern hemisphere, the pole turns to face towards the sun and it gets very high amounts of solar radiation. So different profiles depending on the latitude of the location.